we're going to learn a little bit about wave shaping using the stereo waveshaper and a bevy of other tools that I have over here. The first thing that I want to discuss is how wave shaping is kind of like remapping the volume of a sound. And when I think about remapping the volume of a sound, I usually think about a compressor. So I have a sine wave that I'm going to process with this compressor right here. This is the standard chord compressor, CP1. I have the attack and release times set to as fast as they can go. And the reason I have them as fast as they can go is so I can try to shape individual cycles of a sine wave. There's my sine wave. Right now I have a ratio of 1:1. When I turn it up, we see some shaping going on. What if I have a faster compressor than that? Luckily, I do. I can pop open this M compressor. And actually, for comparison's sake, let's grab this one again. And you'll see that the attack time is 0.1 milliseconds. Go ahead and hit 0.1 for the attack time on this. And then the release time is 1 millisecond. So I'll put this at 1 millisecond. So attack 0.1, release 1. Same settings here. When I turn up the ratio, wave shaping, turning up the ratio, wave shaping. But what if I put the attack and release times at 0, and then I turn up the ratio? It's so fast that it's actually affecting the waveform perfectly. It's exactly grabbing anything that goes above the threshold, and it's turning it down by the ratio. In other words, I've just simply remapped the volume of an individual cycle of this sound, which is causing audible distortion. Well, a waveshaper actually isn't so different. I'll go ahead and just close these out. And I guess I could bypass them. Let me open up this waveshaper to start with. So let me go ahead and I'll put this up, and then I'll have this act symmetrically. So let me grab that compressor again. With a regular compressor, you have your input volume that is then getting attenuated. Stop bypassing this. That is then getting attenuated by your ratio, and then it's becoming your output volume. So, if I have something like 3:1, then anything above 12 dB, for every 3 dB of gain, we're actually only outputting 1 dB to the output. And similarly, with a waveshaper, you have your input values and then your output values. So if I move this parameter right here, I can effectively have a ratio control. So let's see what that looks like if we're not bypassing it. Actually, let me take off this DC blocker. There we go. So much like the compressor was doing, we are exactly attenuating part of the waveform. But there's a key difference between this and a compressor. A compressor is functioning in a way that is acting on the sound in order to attenuate it by a ratio. This is not attenuating as much as it's actually remapping the loudness of a sound, which is, I guess, what distortion is by definition. So this can actually have the ability to go past, instead of having like an infinite to 1 ratio, we can have a flipped ratio. And what that will do is it will actually preserve the momentum of a waveform, but it will flip the velocity of it. So this is acting on linearly on anything any sound that's going in. But then once it passes a certain point, minus 12 dB, it'll react linearly in the opposite direction. So if we see what that looks like, we're chopping off the top of the waveform, and then we're actually changing the trajectory of the waveform. In fact, if I had the waveform at full volume, then once we get exactly halfway up, we flip the trajectory, and halfway up, and then all of a sudden we're flipping. So this is exactly a reversal of where the waveform would be if the volume of it were mapped correctly, but were mapped at 1-to-1 instead of reversed. And that's always going to be happening on the waveform level, as if it was reacting super fast, because it is reacting super fast. It's reacting at 0 milliseconds, because again, it's not something that's functioning like after it passes a certain threshold. It's literally mapping the volume in a different way than what the sound would be doing otherwise. So let's start talking a little bit about the stereo waveshaper and the Kronos. So I can go ahead and I'll just load a preset here. I made the same preset. I believe it's my integers one. Yeah. So you can see this preset looks exactly like this. But there was a key difference here. When I was changing this, you could think of it kind of like a ratio. When I was changing this, when I was remapping the volume after it got past a certain point, I was affecting the top and bottom of the waveform. And let me unbypass that. Let me take off DC blocker for now. So I'm affecting the top and bottom. It's essentially keeping it flat. So once it reaches a certain point, there's no volume change actually after that, until the waveform gets back down to this volume, until it gets back down to that volume, and starts behaving linearly again. In other words, adopting its original wave shape. But I don't have to have it affect the waveform symmetrically. I could have it affect the waveform asymmetrically. And in this way, you see negative percentages and then positive percentages. You can think of these as like 4 quadrants. So now the sound is affected, the positive part of the sound is affected by everything on this side, and then the negative is affected on everything on this side. So the positive sound is actually not getting any gain whatsoever. So if I play it, you can see that it's just flat. And then we get the usual linear response that we're used to for our output. So in other words, we have an asymmetric kind of wavetable. Let me bypass that, and then I'll turn on the Kronos. And you'll see in our oscilloscope that it will look similar, but different. We have the top linear, and then the bottom behaving like we usually see it. But there's a key difference. You see that the 0 point crossing is actually through the middle of the waveform. In other words, it's preserving the amount of power on both the top and bottom. And what the Kronos is doing is it's actually, it has what's called a DC blocker. It's removing DC offset. So if I take off the Kronos and enable this one, you'll see it looks different. But if I have this DC blocker on, then it's doing the same thing where it's shifting the waveform so there's equal power for both the positive and negative amplitudes of the waveform. DC offset has the effect of stealing headroom. So though you're not hearing any difference in sound, you are seeing a difference in your meters. So this is with the DC blocker off. You can see that this is getting awfully close to 0. It actually is at 0, pretty much. If I turn the DC blocker on, we actually get some headroom back. So if you had a bunch of sounds that had DC offset, you'd actually be losing a whole bunch of headroom unnecessarily. And the DC blocker helps protect against that. And luckily, there's one built into the Kronos, so you never really have to worry about it. Like most distortion, it can only create harmonic material. It can't create inharmonic material. So like ring modulation would be an easy example of something that can create inharmonic material. But since this modulation, if you want to consider it modulation or transformation, is simply acting on the waveform itself, there's no other kind of clashing frequency that could possibly create something inharmonic. It's not like you have two operators where one operator is like slightly at a different ratio offset from the other. It's only acting on a single cycling waveform. Thus, everything it produces is going to be harmonic, and I could show that with this one. So if I switch oscillators, let's see, is this sawtooth? Yep. Let me actually turn down the release for now. So with this sawtooth, notice the harmonics. Let me use the other spectrum analyzer, since I could just play something at 100 hertz. So if I play this, it's roughly 100 hertz, and we can see that our next harmonic is 200, 300, 400, 500, so on and so forth. But remember this series. So this series will actually not change, even if we change our wave shape table or transfer function or whatever you want to call it. So let me So I'm running through different shapes. We see the same harmonic series, just with different kinds of emphases. And then if I switch back to a sine wave, you'll see that we are producing harmonics, but again, they'll always be in the harmonic series. There is a way that it can create inharmonic material, and that would be through aliasing, which is very easy to create with something that's rich in harmonics, like a sawtooth. But anyway, let's now discuss what's called crossover distortion. So let me close this one out, and then let me go over and click on, or let me just search for something with crossover distortion here. So crossover distortion is just basically shaping, there we go, shaping that's going on kind of in the middle of the transfer function. So if I play something, then you see that at low amplitudes, the sound is changed there. But what if my sine wave in its entirety was at a low amplitude? Then the whole thing would be shaped by the shape of the transfer function. I keep wanting to call it a wavetable, and actually wavetable synthesis does use transfer functions, but this is about waveshapers, not about wavetable synthesis. So when we have a sound that's not high in volume, you see it is getting shaped over here by this crossover distortion. And then we could boost up the output and have that just be our whole new waveform. So the volume is kind of affecting how the waveform is shaped. And we can use that to our advantage. Like if we have something with a long decay, like I had. So I'll go over and let me turn up the release time of my amp. Let me switch waveforms. And whoops, I was on the wrong one. So you see we have these complex harmonics that are changing. as the sound is decaying away, because the whole shape of the sound is getting changed as it's changing volume. And it creates some really nice kind of shifts in the sound, some really nice like harmonic movement. Again, not frequency wise, but simply volume wise. Now, there is a major difference between the waveshaper that's in Mod 7 and the insert effect waveshaper. That's obviously that this is going to be acting on the sum of whatever you're feeding it, whereas the waveshaper is per voice, per oscillator, actually, in Mod 7. It makes Mod 7 extremely powerful. It's an amazing synthesizer. But anyway, it means that chords will sound very different once they're summed and passed through the waveshaper. So there's a nice trick here that we can do with chords. So here's just a major third. If I go over to the basic vector section in the common tab, basic vector tab, I can change the temperament to pure major. And that'll change how this major third sounds. It's a lot cleaner. So that compared to this. This is right back to pure major. So I really like that. And we of course can change our table to get other very, very interesting sounds. Let me go back to, I like the way this Rezo one sounds. Something that's also neat, if I play two notes that are right next to each other, what you'd usually hear, actually, I'll just turn off the waveshaper. If I play two low notes next to each other, we'll get a beating between the waveforms. And there's a crazy amount of volume change going on there. So if we go ahead and stick that through the waveshaper, it's almost like we get like crazy little like dubstep wobbles. Of course, we can change our table. To actually make that a dubstep wobble, though, would be kind of tricky, since the beating frequency, you would want it to be in time with the song, which is pretty easy, actually, to figure out, but kind of tedious and not really worth it. I would go about making wobbles in a different way. But the trick is still there, and it's still pretty cool. I think I've pretty much covered everything. Of course, there's this post EQ, which we don't really need to go over. Pre-low pass filter, it just low passes the sound before it passes into the waveshaper. It's not actually changing the sound of the waveshaper. It's just changing the sound that's going into the waveshaper. Hence the pre. Yeah. Wow. Did I really cover everything? I feel like I'm forgetting something, but yeah, I think that's pretty much it. So yeah, again, you are remapping the volume of a sound. Straight lines make the waveform behave or display exactly the way it was. Every table in here has a removes DC offset, and then also is not necessarily symmetrical. They all can be. I mean, unless we can visually see that it's symmetrical. A lot of these are asymmetrical, like this one. And it's wave shaping can kind of be thought of as like distortion for different volume levels, which is really great. So yeah, thank you for watching this one, and see you later.